really want you to think about this, because thinking about estimating integrals and derivatives from this like bigger picture really helps you with any questions that you're ever asked about these topics. So derivatives become differences, and there is a derivative at every location of your data point. So if you're trying to calculate the derivative of data, you're going to have an estimation at every data point. So when you do your indexing in a loop, you're going to be calculating a derivative at every I location. Integrals are sums when they're turned into their numerical equivalents. So as a result, it's the area under the curve. So when you're integrating data, it results in a single number. So like with your lab that you're working on, when you took the derivative of the elevation data, you got out a vertical speed for every time that the data was collected. When you integrated the speed over time, it calculates the total distance of that stage in the race, so one number. I wanted to just give a quick review on functions, because I've noticed it a lot, that I think everyone is getting how to write a function, because we use functions for the rest of the semester. So there's a function name which I called AMI. There's inputs that come in that are used in the calculations. The outputs are defined here, and they need to be defined here. If they're not and you call them, there's an error. And so in order to run this function, since x and y are both used in the function, you have to provide the function with those inputs or the code will not run. If you need to know how to use an intrinsic function, this is how you write and call functions that you wrote, you just need to look up the syntax. It's the same thing. You need to know how many inputs there are. You need to know what inputs there are. And there's no way to know other than to look up the help to see how the inputs are defined. That's how you use MATLAB. That's why I have you do it. No one in your career is going to be like, hey, I'm going to show you how to use this function, and like, let me tell you everything about it, and then can you just do it? That's not how MATLAB works. You have to learn how to use the function, and all you have to do is Google it or use the help. I always use Google because the help is always slow on my computer, but they're the same thing. When you Google it, it just goes to the web version of the help, okay? So people are actually doing pretty good with this, but it's just a friendly reminder, because you're going to always be asked to use functions that you've never seen before, or asked to solve a problem which requires you to use a function that makes it much easier to solve. So we're going to be starting interpolation today, and there's really two pieces of interpolation lecture. The first thing that we're going to focus on is the theory of interpolation, which I find that most people find very straightforward. Sorry guys, why do I always unplug that? And that's fine. So what is interpolation? What is it used for? What is the equation? All those kinds of things. But the lab that you're going to be writing for interpolation is to write an interpolation algorithm. So we're going to talk about both of those pieces today, and I'm going to provide you with the full algorithm. Like, I'm going to write it out for you, and you'll just need to translate it into MATLAB code for your lab. So we're on topic 9. So this topic focuses, the lab focuses on linear, is it auto-focusing?
Yeah.
Focuses on linear interpolation, but pretty much all interpolation uses the same algorithm. It just chooses to approximate the point in different ways. So I'm going to extend that in some of this lecture too, but most of what we're talking about focuses on linear interpolation. So what is interpolation? The class that you will use interpolation, it's hard to read. It might be okay with not the computer screen, but yeah, I agree. I usually have these lights on. But isn't it kind of hard to read that now? work together, and anything's possible. So what I was saying is the class that you use, or like not even the class, I mean it is the academic class, but the top, like the focus in mechanical engineering that uses interpolation most is thermodynamics. Because who's taken it? I know a lot of you might be in it or have taken it. Just tables all over the place, right? Looking up numbers, the number you need isn't there, so you have to interpolate between numbers. So it's used all the time. But the algorithm we're writing is a little bit more general. So the idea of interpolation is you're taking data that you're kind of assuming is exact. So think about any thermodynamic property or fluid property, like density, viscosity, entropy, any thermodynamic property. That property depends on the fluid's temperature and pressure and all of these other properties. So if you want to know what the density is of water, you would need to know what temperature of water you're thinking about, right? Because if water's colder, it's denser. But you couldn't measure it infinitely for every possible temperature. You'd maybe have to do it every 5 degrees or every 1 degree. But then you're doing some analysis and you need the value at a value in between the values you collected or you have data for. And that's what you use interpolation for typically. So imagine that you have points like, I'll draw points here at like every 3, you can think of it as every 3 degrees, every 3 seconds, every 3 pressures, whatever it is. But you're looking to measure at some point in between that was not collected. Well, if you use linear interpolation, you're just going to take the average of the 2 points in between, or draw a line between the 2 points that are nearest and find the one that's on that line. And so it's used to make predictions on data sets for values that were not collected, basically. And you've probably interpolated things just by, like, naturally in your life before when you've needed information that you didn't have, like you've estimated the difference between 2 things you did have. And so it is an approximation, and if your data points are close enough, then linear interpolation is always good enough, pretty much. So with a lot of the thermodynamic tables, even though the relationships between temperature and density might not be linear, as long as you have 2 points that are close enough to the point that you're looking for, the linear approximation is fine. So this idea of interpolation is approximation. It's not, it's making do with what you have. And you usually do it because you can't recollect the data or you can't do any better, basically. The other application of linear interpolation, or interpolation, that is used a lot is in modeling. So if any of you have looked at models before, let's say you're solving for pipe flow and you have 100 points in your system. That's what you set up your grid as, and you collected data and you have 100 points. But let's say that wasn't good enough, you needed more resolution. One option is to take the data that you have on all those points and to interpolate them on a finer grid, so now you have 200 points. And the algorithm that you're writing for this lab is more like that. It's doing a lot of interpolation on a lot of points at once, not just having a data set, needing a point in between the available points and calculating one point, because that is not difficult to write a code for. It's just one line definition, right? So that's what we're going to talk about a little bit. So let's first just talk about what the equation is for linear interpolation, and then I'll talk about that algorithm. So linear interpolation, or really any type of interpolation, requires that you have the points that are closest to the point to interpolate from. So we're going to call those 2 points x1, y1, and x2, y2. So if we just draw this up, we will call one of the points x1, y1, and the other point x2, y2. So if you have the 2 points that you're going to interpolate from, all you need is the relationship to define any point in between, right? So let's say that you had this data and now you're like, okay, I know that I need to use these 2 points. What's the equation to locate the star that I have drawn in between? And so the way that pretty much all books and textbooks and algorithms indicate the one in between is we use the syntax or the notation star. So star is the interpolated value that you're looking for that you don't have. And the thing to keep in mind is that you always know the x location of your star value. That's like the temperature you're looking for. You have temperature at 5 and 10 and you're looking for the value at 7 in between. So you always know all the x values, and what you're trying to locate is where that value is on the y-axis. So that would be the y star value. So that's what the interpolation formula solves for. So all you have to do is create or write out the equation of a line between x1, y1, x2, y2, which you can all do, because that's algebra, right? You know this. We did this. You've done this. Create an equation of a line. Should we just take a minute to do that on our own, or you want me to show you? You know what you can do? You can either, remember, did you memorize the formula like y minus y1 equals m times x minus x1, and then you just have to calculate m? Do you remember that point slope formula? That's all you need to do this. If you can't remember that, which is, you know, who thinks about this all the time besides me, you could also just remember like triangles. That one's usually pretty easy for people to remember. So if you just make 2 triangles, one triangle here and one triangle here, they both have the same angle. So you can use SOHCAHTOA to relate them. I don't know why I'm like talking so philosophically about this and not just showing you how to do this, but do you all know how to do this? Like if you had the moment, you could do it, right? So I can just write out the final equation. Okay, so similar triangles, that's how I'll show it to you. Similar triangles. This is the same angle in both of the triangles I drew. I'll let you kind of think about this in more detail, but if you just compare the 2 sides of the triangle, oops, that's a 1. 2 triangles, compare them, y2 minus y1 over x2 minus x1. That relates points x1, y1, x2, y2, x star, y star. It would be the same as using the point slope formula. So all you need to do is solve for your only unknown in this. Remember, y star is your only unknown. Yeah. And this will be your formula. And this, you can see, is the point slope formula. Once you rearrange it, just the y got moved over. So as long as you know the 2 points that bracket the point that you're trying to interpolate, you can take this formula and it can calculate any interpolated value using linear interpolation. So I think that's usually pretty straightforward for most people. This is a choice. This is linear interpolation. There's a lot of other options. You could just say, always use the point to the left. Always use the point to the right. Always use the closest point, or always use the average of the 2 points, or linear interpolate. There's unlimited options for what you could do, but this is the linear interpolation option. Okay, so what you guys are going to be doing in the lab, you got this formula. This is linear interpolation formula once you know the 2 points. But the trick of the algorithm that you're writing in lab is to find the 2 points that bracket the point that you're looking for. That's the trick of a interpolation algorithm. So in your lab, this is what you're going to do. The way your lab is set up is you have data that was collected for solar panel, or solar radiation really, and it was collected at every hour it was collected. So just imagine if I draw out just a few points, you have like here, 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 and here, where this is 1 hour, this is 2 hours, this is 3 hours, and this is 4 hours. Imagine, this is not real, but imagine that you needed this data at every minute. So you needed to have all of the minutes in between every hour. You're going to write an algorithm that can basically take any set of data and interpolate it on any new set of t values. So it's basically going to just take and fill in all the minutes. I can't draw 60, I didn't leave enough space, but all the minutes in between, and they'll be linearly connected between each hour. So your final plot will just plot your original hourly data and then a bunch of points in between. Okay, so that's the goal. And the code should be able to take any x value, any f value, and any x star value and interpolate on that new grid. What's that? New data set, interpolate to a new data set. Yeah, I write too fast. So to do this, you're going to write what's called the window interpolating algorithm. So I'm going to write out what the algorithm is, and I'm going to use like a really useful set of data that's super applicable to life and reasonable to think about, which is the number of texts sent per month versus age. So if you didn't know, the older you are, the less texts per month that you send, according to data that I've actually researched. It's not, I didn't make it up. So for example, if X is the number of texts sent and received per month, and then Y is the age in years of individuals, then if you were wondering how old someone was, you could just find out how many texts per month they have, and then you could interpolate to find out how old they were, and that's really the most practical way to find this information, I think. So, X data, let's think about this. This is the data that I collected. A 19-year-old, on average, sends about 2,000. A 75-year-old, 100. These are specific people. Like that's Fred. This is Peter. This is Julie. What else? 16-year-old sends 3,500. How many do you guys send and receive? Because when I did this, I was calculated as like an 80-year-old or something, according to this data. So just imagine. So let's say like, oh, I just found out this person sends 2,000 texts. How old is that person? Interpolation will tell you. So what we're going to do, though, is write an algorithm that, given these texts that you found by doing some investigation. So this person sends 151. This person says 1221. This one sends 3609, 775, 5,000. We are going to write an algorithm that finds how old each of these people are based off of the XY data that's completely factual, dependable. So this is what you need to do. This is the algorithm. I realize that I never write the H in algorithm, but you know it's there. So the first step is you need data to start with. So you need to get the X and Y data that you're going to interpolate from. This can be you can get this through reading in a file, inputting a file. It's whatever it is that you have. Next, if you're trying to find, for example, the age of someone who sends 151 texts, how would the data need to be structured in order to find that? Does that make sense to you? So like if you're looking through, you're like, oh, okay, this one's bigger, okay, but this one's smaller. Is there any that's smaller than this? How could we fix that? Yeah, the data needs to be sorted. So your data that you're using needs to be sorted by the X data that you're looking for. So we're looking by X data, so we want X and Y to both be sorted by X. They can be descending or ascending, it doesn't matter. And when you're programming this in your code, you can use the intrinsic function sort. You don't have to write a sorting algorithm, although sorting algorithms are really fun. Okay, so then logically, if you're just kind of working through this in your head, you're going to think about, okay, let's look at the first X star value first, so 151. And once we have our data sorted, we're going to find which to bracket that first X star value. So we're going to call that a window or a bracket. And that window is just where the X star is greater than the point on its left and less than the point on its right. So if you like put it right into the data, it would fit in that ascending or descending order depending on which way you did it. So you have to find those 2 points. So you already have written lots of find functions, right? So find functions are typically for loops with an if statement inside. So that's what you want to kind of think about. Once you find the window, then you're just going to use the linear interpolation function, or equation, sorry, that we just derived very rigorously to approximate y star. So y star is just going to equal y1 using these two same points that I've labeled here. And then the slope, it's not exactly the slope, actually this is the slope, but using that formula there. So you already know x1, y1, you know x2, y2, and you know x star. So the entire right-hand side is known, so you can define the y star. So we just did that for one x star value. So that was step 3. So now step 4 is to just repeat step 3 for all the x star values that are in the x star array. And so however big X star is, you will have a Y star array that's the same size, and you'll just fill them in one at a time. And then once you finish getting every Y star value, the end of every sort of like thought algorithm is, you get something at the beginning and then you need to report something out. So that might be an output, that might just be a plot, it just depends on how you structure the code. So let's treat this entire algorithm as a function that can receive any x, y, and x star and output any y star. That's how I'm going to write this. So this first step is going to be the inputs to the function, x and y. Step 2 is just going to be applying the sort function to your data. This first step 3, x star is also going to come in as an input, so that means you're going to have 3 total inputs, x, y, and x star. The find algorithm, I already told you. What is the numerical equivalent? What structures do we need to use in order to write a find? For and if. You also can write this with a while loop, that's possible, but you've already written something very similar with the same structure. It's very similar to the planets algorithm that you wrote where you located planets with specific conditions. It's the same idea, it's just that this is your condition now. So you're going to loop through all your x points until this is true, basically. What is this? This is just a definition. So it's just going to be y star equals. However, this is going to be an array. So you want to set up x star to be the same size as x star outside of the loop before you start doing anything. And then inside the loop, you'll need to index y star. And then if you see repeat, what does that mean? Repeat means loop, yeah. And this is repeat for a set number of times. So a for loop will work because we know how big x star is, so we know how many times we need to repeat. So that means that a window interpolation algorithm has 2 nested for loops. But what's different is you've done nested for loops, but those nested in a way that it would go through like a 2D space and get every ij combination, but this is very different. One loop is going to loop through your x stars. The inside loop is going to loop through your x's to find the window. So that's what your goal is to get that, and then the only output of your function is going to be y star. So this will be a self-contained function that can interpolate anything on any other grid, and then you'll have an outside 9, and that will import your data and then call this function. It's probably best when you're writing this function to try it on simpler data. Just make some up and then interpolate it on a different grid. But you can try it on the data, it's just a lot more complicated. Does anyone have any questions about the algorithm? No questions? Okay, so I think that's it then. So see you guys in lab.